Excellent. Now I'm recording. Excellent. So how's everyone feeling about their conversion of their Java code to C code? Everyone feels pretty good about that at this point? Was that no? Was that a challenging endeavor? Did you learn a lot about C, having to take Java and turning it to C? So we had talked a little bit about how we're gonna go ahead and submit that. I usually do assignments, homework assignments for those of you who had taken me before, or if not, maybe heard word. Usually I do homework assignments and I'll use tests as check-ins. So at some point, I'd like to check in with each of the groups and just see what you've been able to execute and just get a feel from you about what your approach was and how you were able to solve that problem. And if not, what obstacles you ran alongside the way. So I had mentioned Monday was going to be the time that I was going to talk about how we were going to deliver this kind of student challenge, and it's going to be in congruence with the way that I typically do the examinations. So I'd want to go ahead and touch base with you. We could set up like a chat through Zoom, and one person can designate themselves as like the controller, where I'll let you go ahead and share your screen, execute your app, show it off, and then collectively you as a group, unless you're solo, in which case you were your own group, can kind of explain to me how you went about solving the problem. And that way, that just gives me the ability to check in with each of all of you to make sure that everyone's on the same page and we're kind of progressing where we'd expect to be at each time. And also, again, one of the big things, I don't know if you went to the meetup last Thursday where the chair was there, where the undergraduate coordinator and the graduate coordinator was there. But one of the big things that we're always striving to do inside the curriculum is to have you develop the ability to not just develop software, but talk about developing software. It's just as critical that you know how to discuss your processes of problem solving and talk about what you did as it is to actually do those things, especially if you intend to go into industry and work side a team of people. And so these kinds of abilities for us to kind of check in allow you to think deeply about what your problem solving task was, what obstacles you ran into, and what your solutions were, and be able to talk about them in English, right? In a way that you can express them in a way that's meaningful to me without just like pointing at code segments. Does that make sense to everyone? Now, there are some of you I know who had reached out to me on Discord. I got super busy over the weekend, way more busy than I thought. So I'm going to start checking in on those Discord messages and following up with everybody over the course of after today's lecture and for the remainder of this week. So if you were having issues either with the first lab, which I don't think is due until next Monday, right? Is that what I made? Is it due today? I'll push that back then to be next Monday. Although you probably don't want to wait till next Monday because that's like what, Lundy Gras? So no one wants to work on Lundy Gras. It'll be due then, but you should do it before then. So that's the nice thing about setting the delay time on that. That'll give me the chance to check in with the students who had reached out for help. It gives me this week to go ahead and help those students out to make sure everyone's on pace. Excellent. Okay, so any questions besides that? Are we good? Excellent. Well, I can't wait to start seeing what some of y'all had start to put together in terms of your to-do application and hearing some of the challenges you've encountered along the way. I want to spend today's lecture moving to the next chapter. So as you might recall, last week we went through effectively, so far up to this point, let's talk about where we're at, because we're like a month into our semester so far. So far, we've covered all the critical concepts inside the PDF, the essential C, right? And so we went through 49 micro examples of C code that brought us all the way to the point where you then were given a challenge of converting some basic Java application into a C application, right? And using those little micro code examples, you should be able to modularly fit them into a way that you can create something that's actually pretty impressive as in terms of your own first C application. So after that, we then took a tour of what a computer system is, because recall, this is a systems class. So we had to go through all of all of the definitional concepts of what defines a computer system, both as a software and as a hardware framework, and then how we can go ahead and inspect the nexus of that, the emergence of those two things into our computer system. And so that really is what tied us into that very first lab, or I guess our 0th lab, our lab 0, our introductory lab, which actually covers a lot of concepts. It covers concepts related to programming in C, and it covers concepts as it relates to how your source code file is converted, translated, transformed into an application. And what, in fact, the GCC compiler is, it's not just the singular thing, but it's doing a lot of different staged processing of a document into an intermediary document, into another intermediary document, into another intermediary document, until finally it is a executable object, right? And so at this point, after you get through the first lab, we can start talking about what you're going to need for the next lab, lab 1, which is typically referred to as data lab. And so lab 1 is really goes into these concepts that, if we're following the book, is going to be chapter 2, representing and manipulating information. Now, I've started to try to beautify these slides because I made these slides in their entirety last semester, the first time I taught this. Didn't quite finish beautifying these slides, so some of these might be a little ugly, and I do like to try to go into real life practical examples along the way. Can you please close that door for me as well? Thank you. So today I kind of just want to spend our time introducing the concepts in chapter 2. So in chapter 2, now that we've had an overview tour of a computer system, let's start talking about going in detail about how we represent and manipulate information in a computer system. You need to have a strong understanding of this if everything else is going to make sense in terms of how we can do systems programming. Okay, so a quick abstract of some overview over what we're going to cover over the course of not just this lecture, but all lectures that kind of contain towards this particular concept, this chapter. We're going to look and inspect in computer arithmetic. So we're going to see how we can handle both unsigned and 2's complements numbers. Now, I'm going to try to check in with all of you here. Is this something that you've already covered in assembly, this concept? Oh, good. So that's what I'm banking on. And so there's a lot of slides that are there. I'll try to be as brief or verbose depending on how much you've covered in an assembly, because I don't want to rehash too much if you already know it. But if you don't know it, I want to kind of go into a little bit of detail. Okay, what about value range? Did you go over the range of values based off the word size in assembly? Because that's going to be something we do cover inside this chapter as well. So that's going to, so like for instance here, we'll talk more about it when we go into here, but on our systems, and I might have already referred to this in a previous lecture, even in this class, there's a concept of where you might have a 32-bit system versus a 64-bit system. Having an understanding of what that maps to the system itself is kind of a meaningful thing you should understand, because it has real practical implications on how we can store, how we save, and how we represent data inside of our system. Casting effects. So we're going to talk about the impact of converting between signed and unsigned numbers. So I'm sure you covered the concept of signed and unsigned numbers. Did you do any of these by hand, or was this something that you'd expect inside of a debugger? Did you use a debugger in assembly? Oh, excellent. So y'all have some debugger experience as well? Oh, that's very good. That's going to be very good when we get to Bomb Lab. Okay. The arithmetic properties, so the mathematical characteristics of arithmetic operations. I'm sure y'all covered with shifts, and again, we'll talk about it, but I'm going to get a feel from your faces how quickly I can go through some of this content. Bit level operations. Of course, we're going to use C for demonstrating Boolean algebra, but usually a big concept of how we manipulate and store data is all about its Boolean representation, its binary representation. Binary representation allows us to use Boolean algebra on it. And then floating point representation using the IEEE floating point format, and how that actually goes ahead and is able to save your data, and how precise is that data? Well, we're going to take a look at all of that. So again, the motivation behind this entire chapter, so that by the time we're done chapter 2, you should fundamentally, foundationally know how all information, all data, regardless of what it's typed to, is stored inside of a computer system in a binary format. And so if you know that, and then more particularly when we start drilling down into some of the data types that we're going to be more concerned about in terms of C programming, it's going to be a deep examination into how numbers are represented and how we can use the set of numbers and do arithmetic operations to get results. Well, there's some things that could lead to pitfalls if we were unaware of how our numbers, how our integers, how our floating points are actually represented, where we might expect a certain behavior and we get some different behavior. So for instance, if we assess if one number is less than another, should we opt for saying X is less than Y, or should we say X minus Y is less than 0? Are these equivalent? Maybe logically they are, right? You might not see a reason to pick one versus the other, but by the time we're done, these representations, you might see one might give better, more predictable results than the other in certain circumstances. And we're going to motivate this. We'll actually see instances where one of these will break and the other will not. Okay, let's think about some other potential pitfalls that we can have just due to the underlining representation of information in our system. Given the asymmetric range of 2's complement representation, Y might minus Y less than minus X introduce errors, create exceptional behavior that we might not expect. Again, we're going to see instances in code where we can actually break this. And then finally, in comparing floating point values, what consideration must be made to ensure that you get both accuracy and reliability versus, say, for instance, integers? So what do I mean by this? Suppose you want to do an equality check. That's where you're checking for if one floating point is the same as the other, right? Might this be problematic? And if it is problematic, if you can't necessarily guarantee that you can do an equality check against 2 floating point numbers, how do you resolve that? How do you check for equality then? So when does it make sense to check for equality on numerical values? And if there is no assurance, what is the next best way for checking equality? We're going to discuss all these concepts kind of organically as we go into the mathematical operations that we can perform on our data. But before we get there, let's not jump too far. Let's just kind of break down the entire lineup of what this chapter covers. So today, I'm just going to delve into information storage. We're going to kind of slowly ease into it. And then next lecture, we'll then dive into integer representations and integer arithmetic. And depending on how comfortable you're with that, will depend on how quickly we go through that. And then finally, we'll have a lecture where we spend showing how we do floating point representation. And then that'll pretty much be our chapter 2. By the time we get through that, I think you should have everything you know to be able to do the first data lab. So what I'll probably do soon is unlock the first data lab so that for those of you who are now done with lab 0, you have something else that you can tackle into. And again, I also have my lectures from last semester available. So if you want to jump ahead, you're afforded that opportunity, right? You can actually fast forward in time and see what the course content is before we actually get there. And the nice thing about recorded lectures is that you can do it like 2x speed. So I think that's certainly the way to consume content. Okay, so let's start with a little preface. Before we get into the content that's actually provided by the book, I'm slowly adding my own content and my own set of slides to try to motivate what the book provides. And don't get me wrong, I think the book is wonderfully written. I think it's very approachable. I think it's one of these, and I think I stated this on the very first day of class. I think it's a student focused textbook, which means that you can parse and read through it without necessarily me having to explain the content. It's brought down to a level where it sets up all the premises in a way that you should already be able to understand, and then come with the concluding motivating ideas from what's given to you. And then the labs only kind of go in and fortify those knowledges by giving you some really good challenges. But with that said, I think every now and then there's some holes that I want to patch in. So these are some of these concepts that I just want to make sure that everyone's on the ground floor with. So when we first start looking at systems, computer systems, before we're well acquainted, before we're trained in it, there's an illusion that we see with computers. This illusion is that they create these digital replicas of our world that has sounds and pictures and graphics and numbers and text, right? They look like these really magic boxes. But the truth is that at the heart, computers are just built from a simple on-off switches, millions of them, right? So that's all a computer is. So if that's what it is, then the real magic that we see is being able to convert our real world data, the sounds, the pictures, the numbers, whatever, into a binary format, into binary data that the switches can then model, that they can represent, right? So this is what the true motivating factor of what we're going to cover in this chapter is. How do we take this, no matter what it is, whether it's a PNG, a JPEG, a .wav, a .mp3, a .mp4, right? And then translate it into something that can store into our system. So you have all these different data types that all end up having binary translations of. So the first thing that we should really state then is that computers are electronic machines. What does that mean? What's an electronics approach? Computers use electricity. Seems obvious, but we're going to go there. They're not mechanical. That's the important part. You think mechanical, you think gears. You think of physical, right? Mechanical operations. We don't use mechanical operations on computers in order to capture our data processing and our storage. What's the advantage of using electricity? Speed, right? There's a reason why computers are so fast. They operate at the speed of, well, electricity, which is damn near the speed of light. Electricity is plentiful and moves fast through wires. It's reliable, so our electrical parts are more reliable than mechanical parts since they require no moving parts, right? Okay, so let's talk about the electronics explanation. Underlining, so if we're saving things in a binary state, why is that? Because we have this switch functionality. Electricity can flow through switches. If the switch is closed, the electricity flows. If the switch is open, the electricity does not flow. So there's two states, and we can actually evaluate that state with within our electronic system. So with binary coding, what we do is we process data in the computer, and we need a way to represent the data in the switches, so we use a binary coding format for that, because there's one of two states. You can almost think of that as a finite state machine that we model. Okay, so to highlight that first slide, which seemed very obvious, let me say something that's nuanced, probably obvious, but it does introduce confusion the way that computers are usually communicated to the general masses. Computers are not mechanical machines. That's why they are electronic machines, right? So let's talk about the difference between mechanical versus electronic switches. So the common misconception when probably, and let me know if you've ever experienced this. This is what I experienced when the explanation was first given to me. The idea that a computer saves state like something like operating a physical light switch, like this is on and this is off. This is on, this is off, right? Has anyone kind of illustrated that concept? It's like, yeah, look, we have a binary state. I switch the light position in one position, and now I'm in an on state. I switch it in the off position, and now it's in an off state. And I can see the position and say, oh, I can now see the light's on or off, and that gives me an encoding. And yeah, conceptually, that does That is what's working, but it creates a misconception that there's something mechanical happening in the system where you're turning things on and off, right? That's not what's happening. Nothing mechanical is happening in this system, right? You're not flipping on and off actual switches. You're using what's called a transistor, which is an electronic switch. That allows you to use electrical signals to turn on and off. And that's why we can do it so fast. If we're mechanically switching, computers wouldn't operate like they do. They'd be far too slow. They'd produce a lot more heat. They'd be much larger. The reason why they're so small, they're so cheap, they're so quick, is that electricity is super plentiful. We can just put as much power into it. It's super fast, and we can make it microscopic. So this idea of switches is a good one to motivate that as a binary system, but I think it's important to understand that when we talk about switches, they're actual real physical switches, but in the form of transistors, which uses electricity to be able to set and unset them. And then we can evaluate based off of how much resistance or how much voltage in the line, whether it's in an off or on state. So we can check the state of each of the switches, which is what we need, because checking the state of the switches allows us to know what is the representation of a given switch. And so just to give you a basic idea of how a transistor might operate in a non-mechanical way, I have this GIF here. So the two GIFs are to motivate. Notice what it means to have mechanical movement dictate whether your switch is in an on or off state would be like this Frankenstein switch on this like 5th grade science experiment, right? Where it's in one position, it's on, in another position, you close that circuit and allows that light to come on. We can do the same thing. Notice here, we're in an off position, and once we apply this charge here on the gate, we get the flow, and that creates an on, and that's effectively what's happening. So if you just wanted to elucidate how the hardware is modeling the switches, that's how it works. Okay, so now we talked about how hardware switching actually works inside of computer systems, how we use electronics and not mechanical influences to be able to do our switching and what the importance of that is. Let's talk about switch states. So again, the important thing here is that the switch states at the end of the day resolve to two distinct states, an on and an off. And so the beautiful thing about that is mathematics has already defined for us a binary number system, a number system that has two countable units, a 0 and a 1, right? And so we can then map our binary counting system onto the two states that a physical switch can have, or an electronic switch. Still a physical thing, but it works electronically. So we'll map our digit of 0, our off state to be 0, and our on state to be 1. And so whenever we say we have a bit, a binary digit represents our basic unit of data, one of two states that can be recorded. And so that would represent a single switch's state. And so clearly in modern computers, we have millions, if not billions, of switches, so that we have millions, if not billions, of bits that are available for encoding or storage or processing, all the same or similar. Okay, so let's talk about bits and building a binary language then. So we can think of our bits then as effectively a binary character. When I say character, similar to a character we have in our alphabet. So when we go to represent information in the form of English words, we have a set of alphabet that we use to construct our words from. And so our base units in English would be the letters from A to Z. And then we can combine those in a variety of ways to create words that have specific meaning in relation to one another. So for instance, the word cat and the word dog are a combination of those letters, but they represent, based off of context, a particular thing. So the same way we can be very expressive using a closed set of alphabet in order to start mapping into more complex concepts. We do the same thing by building a binary language. We can create a single bit as a character to start creating a bit sequence that we will refer to as a binary word. One or more bit can form a sequence of bits that can then be encoded based off of some context to represent something in and of itself inside of a closed set. So inside of that set of bit sequences, each one has a unique meaning, kind of like a dictionary. So in this instance, we're just showing what size binary words we can form. The 0 and 1 are both 1-bit words. You can only map 2 different meanings to a single bit. We have a 4-bit word. And then finally, we have an 8-bit word. The 8-bit word is kind of special because bytes themselves are going to be the smallest addressable memory unit. Let's explain why that might be the case. So a byte can be defined as 8 electronic switches, each representing a bit. So let's look at like a visualization. If this represent our on and off switches, right, inside of our transistor, we can easily encode the on and off states into our actual number system of zeros and ones. That seems pretty self-evident. Now, traditionally, a byte was the amount of bits, so 256, 2 to the power of 8, needed to represent a single text character. So if you wondered why is byte 8 bits the smallest unit of addressable space, that was the motivation. What is giving a binary sequence? So if we start talking binary sequence, you have 1 of 2 permutations at for just 1 bit, right? So 2 to the power of 1 is 2, right? 2 to the power of 2, that's 2 bits, is how many different permutations? That's 4, right? Not enough to map all of the characters that we need to represent in a computer system. What's 2 to the power of 3? That's going to be 8, right? Still not enough. What's 2 to the power of 4? Not enough. What's 2 to the power of 5? And what's 2 to the power of 6? And 2 to the power of 7? Yeah, so even 128 is enough if we need to represent all the upper case letters, all the lower case letters. If you think of all the special symbols like the apostrophes, the quotations, the single quotations, question marks, exclamation marks, null characters, right? Like the bare minimal that we needed way back when the hardware was first being designed, because they're trying to limit, it was very expensive to create memory. So the question was, what's the smallest amount of memory that we can use to encode a character, all the characters we need access to? And so it was 2 to the power of 8. So, and because standards never die, that is still the smallest addressable space that we use in today's computer. Now, that doesn't define the word size, because byte is just the smallest addressable space. It's not the largest amount of space that we can process on. So it just means that every register, so every time we save an entry, the motivating idea is, can we save it as a character? There's a reason why the character is one byte. That is the very reason why bytes were selected to be that thing to begin with. So it's more or less the characters motivated 8 bits and not 8 bits motivated having that character data type. Just a little rationalization for you, and that all aligns with the ASCII standard. Okay, let's talk a little bit about memory addressing. So we talked about this led to the byte becoming the smallest addressable memory unit in many, like you might have some like outlier computer systems, but almost all computer systems, we now define all of our data measurements in terms of bytes, right? To the point where in practical applications in computing, all data sizes and storage capacities are measured in bytes and multiple of therefore. So like kilobytes, megabytes, gigabytes has some universal measure for measuring how large data is that's to be processed on. And again, the key concept here is a single byte can encode a variety of different data types, right? Because that's just the sequence. So the sequence has to be meaningful depending on what we want to translate it as. So this binary sequence can be translated, say, for instance, maybe into an integer. If it's translated into an integer, it might be the number 67. If it's translated into a character, it might be the letter C. If it's translated into the sound, it would be whatever the 67th decibel inside of the sound dictionary would be, whatever that might be. If it's in an image, it could indicate the 67th shade of a particular color of a pixel, whatever that might be. Or it can even encode an instruction that we're trying to go ahead and request for our processor to execute on. So that same binary sequence, given a particular context, and again, in systems, you've probably already experienced this, because this is why a lot of files have an extension attached to it. It gives the system context as to how to read the binary data or that text data, depending on what that extension is from that file. So like, for instance, .txt, .doc, .ppt, right? .wav, .mp3, right? These are all just certain file types, and you, without maybe being formally instructed in it, can look at the extension and know the context of what that file is used for. You look at an MP3 and you're like, oh, I can hear music from that. You look at a .wav, also a music file, right? MP4, video file, right? AVI, video file, right? PNG, image file, JPEG, image file, TXT, text file, a .java would be a text file, but .class would be a binary file. So just like you can look at an extension and understand the context by which what application you would use to open that. So you do data processing in a way. If you have an MP4, you might use something like VLC player, right, to open it up. You wouldn't use a sound editor to open it up. If you have an MP3, you might use a music player application. If you have a TXT file, you can use that on VLC, like, or a video player, you'd use a text editor. So naturally, the same way that the context of the file lets you know what application to open it in, well, that's also how the underlying system knows how to parse that file. So every one of these applications will read in that the binary data there in a different way and parse it in a way that's meaningful to that application, so it can reproduce the entire thing it was designed to say. The underlying data, though, is nothing but binary stuff. And you can open up that binary stuff with anything. But if you want it to open up in a meaningful way, you have to understand the context it is authored. But the big point is how expressive using binary sequences are. So we know, we live in a day and age where we know we can have all these files on our computer system, that we can use all these variety of applications to open up these various files. But the big takeaway is we've been able to design a system that can save all these different kinds of formats in the same underlying fundamental kind of type. And then they create their own kind of binary language on how to parse it into its own meaningful set of words to then express it in the way that it then executes inside of our computer system. So our bytes represent our building blocks. They're super adaptable, and they can take as many different forms as we want to encode to them. And just some examples of this, we have the ability to map our decimal number system onto a binary system. We're able to map our alphanumeric characters or glyphs to a bit pattern, bit sequences that then map into a binary sequence. And so, again, the motivating idea about using 8 bits is that then we can start grabbing things from a keyboard, sending that to the processor and storing that directly. So we can start capturing interactions with the end user. One of the powerful things about representing characters in bytes. And then we can take sequence of inputs and encoding one at a time, back to back, all with their each expression. or bit patterns. So again, this is how we're building a different set of binary words. So once C is mapped to a particular binary sequence, that sequence inside the context of characters can't be used for anything else, right? So that represents the binary word for C in the context of a car. And so very similar to then defining uppercase A and uppercase B and lowercase a, lowercase b, all the ones that would be, say, for instance, defined in here based off the ASCII standard, which has then been expanded to the UTF-8 standard, which has then been expanded to the UTF-16 standard. What about colors? So the way that images are typically saved inside of a computer system is based off of pixels. Pixels is short for a picture element. And so typically every pixel can have one of three values: a red value, a green value, and a blue value. The way that our displays work is you can combine those three primary colors. So in light theory, our primary colors are red, green, and blue, right? In contrast to pigment theory, paint theory, which is red, yellow, and blue. So given the way that light works, we can combine those three primary colors, just like in paint theory, where you can take any primary color in paint theory and get any combination. Combine them to get any color from that. It's the same thing with light theory and color. So by representing a set of values for our red, and our red, our green, and our blue, we can then, in a two-dimensional or tabular format, because we have two-dimensional displays, we can then express effectively as a two-dimensional array of reds, greens, and blues, express any kind of picture value. So that allows us to translate pictures into numbers and then numbers into binary values, right? Our red value is mapped between 0 to 255, a byte. Our green value is mapped between 0 and 255, and our blue value is mapped between 0 and 255. But hey, you combine that many, that's how you get 16 million different colors, which is more than what the human eye can actually discriminate against. And then sound, again, something that seems ethereal, like the idea of graphics, like images and sound seem like ethereal things that you can't map to numbers. Numbers make sense. Characters make sense because we expressed it, but we just talked about how we can map the concept of an image to a set of numbers. We can do the same thing with sound based off of its frequency. So keep in mind the way that sound populates, the way that sound actually manifests itself, it's the movement, it's the waves of air around us. And so based off of the amplitude of the waves, we can actually encode it. We have mathematical functions that are useful. Well, they're useful in defining the way that electricity flows, but guess what? It's also useful in defining the way that audio flows, that sound waves flow. And so we can reproduce a wave based off of a set of numerical values. And then we can store those as a set of decibels or inside of effectively an application that's designed to have a dictionary that can play a bit of unit, just like you have a pixel element. I don't know what the sound elements are called, actually. Does anyone know what like the base unit of sound in a computer application is called? Just like it's in a imaging application, it's a pixel. If it's an undefined piece of data, it's just a bit, like a binary digit. Is there a definition? Oh, hertz. I think actually you might be right. It might be the number of hertz is the base unit. And then you ascribe to some hertz value. And then as you're increasing and decreasing, it's going to go ahead and create a different tone. And then you sequence that together, and guess what? All of a sudden you have something that sounds like a song, or it sounds like someone talking. It might even sound like it's you talking. It's very impressive the way we've been able to map everything around us into the format and represent it as nothing but numerical data, which then can be archived and saved or and processed as binary data. And again, we've talked about this a little bit before, but this is a good topic to revisit this. We can go ahead and also represent our program data in the form of bytes as well. So for instance, suppose that we had this program here. Well, each one of these keywords that the system would use would have some memory address, or it would have some representation in binary that when it's parsed in the system, it has a meaning. So even the application logic itself has a binary representation inside of our computer system. Okay, so those were the slides I had pieced together to add on towards the ones that are in chapter 2. So that's going to motivate us then to start covering the concepts that we first speak with, where bits plus context represents binary representation. We already mentioned how computers store and process information into valued signals, and that we use a base 2 numerical system. We talked about why context matters, because we can have identical binary sequences, but based off the context they're supposed to be utilized in, whether it's supposed to be music or imagery or computer code or data values, is going to determine how we translate that binary sequence. And so the power of the reason why we get such a high adaptability we see is that if we combine context, being able to contextualize anything however we want with binary sequences, we can then represent any an element of any finite set. And then the world really opens up to us on what we can then store. So for the purposes, though, of what we really care about inside of our system, at least in order to do most of the processing work that the system has to do, the types of data that we're going to be most interested in representing is going to be numerical data, right? Especially if all other data types that we end up encoding in our system has a numerical analog. Right? We mentioned how images can then be broken into a vector. If you've ever heard of a vector, it's a group of values, of ordered values. So like, for instance, the first vectors you probably that you probably worked with are coordinate spaces, like an X and Y space. You always read the first value is X and the second value is Y in a Cartesian coordinate system, right? Effectively, what you were working with is a vector, a set of vectors which represent your x-axis and your y-axis. Why do I bring that up? Well, I'm referring back to when we're talking about how do we encode our images. It's a vector of a red value, a green value, and a blue value. How do we encode our music? It's going to be a set of hertz values or decibel values. Okay, but so if everything then has a numerical representation, then it's important for us to really understand how is numerical values represented and processed on our computer system. So that's what we're going to talk about. There's a couple of different encodings, right? We have our unsigned encoding. And so this is based on a traditional binary notation. So in an unsigned encoding, the key word of unsigned, it means that you don't have a plus or minus sign ascribed to the number. That means you start the number set at 0 and you only go positive, right? There's no sense of a negative value in an unsigned encoding. Now, clearly, we want to represent the ability to have negative numbers. And so we've developed a way to use a different encoding on our binary sequences to do that. And that's going to be the 2's complement encoding, where we can use a set of rules that allows us to represent whether the leading value of our binary number is negative or positive. And so we represent these in 2 different ways. And it's important to know what representation you have at any given time. And then finally, the other type of value. So the first two that we talked about in particular are integer values. Those are discrete values. And so let's talk about non-discrete values. Let's talk about why the concept of calculus has very practical, applicable concepts that we want to be aware of. So in integer data sets, discrete data sets, it's scoped well so that you have one unit of, say, 1, and then 2, then 3, then 4, then 5, right? And so you have some potentially unbounded set, but since we're limited to a number of bits, right, we do have bounds on what our min and max values are. We'll talk more about that when we talk about representations, but the idea is that there's nothing in between. They're not infinitesimally small between each other, right? So there's a discrete step level that you get as you progress in a numerical integer set. In floating point representation, there is this idea of infinitesimal precision, where you can actually take a fractional value based off of a radix point. So you have your radix point, usually in a base 10 system, you'll call that radix point your decimal point. So you have your decimal point, and then you could say 1.5, and that's expressive. That allows you to say, oh, that's 1, but also like half of a unit as well, if we're thinking of it as unit steps. Or you could say 1.25, or you can say 1.0003. So this idea of a floating point number really borrows from some of the concepts that you have covered or will cover in calculus, because what you're really striving to capture with floating point numbers is the idea that you can have an infinitesimal difference between two things, represented by whatever that fractional value is. And it can get infinitesimally small, right? So it can start at, half, right? And but then if we have that, it's a quarter. You have that, that's an eighth. And if you have that, it's a 16th. You have that, it's a 32nd. You have that, it's a 64th. And it keeps getting smaller and smaller and smaller. And that should be unbounded, right? You should be able to infinitely take a halfway point in a system that represents a continuous system and not a discrete system, and be able to distinguish until you define some rule of convergence, where you get so small, it doesn't matter anymore. They're effectively the same thing. So if you ever wondered, why is calculus valuable? There you go. Every time you use a floating point number, you're using theories that are put forth by calculus. And it had anything then that you start modeling that uses fractional numbers and not integer numbers, you can do some powerful calculus with to go ahead and ascertain a result. It's just the way we even represent those numbers is really based on being able to define infinitesimals. So we'll talk more about that when we get into our floating point encoder. And then, of course, we have this concept of overflows. And so we will actually try to look at some example code of what it means to overflow. Did y'all do that in assembly by chance? Like actually see your numbers overflow, at least cover them? Good. Okay, so that's our preface. Okay, so now let's actually go into this concept of information storage. Now, I'm going to try to go through the slides. I pulled this directly from the textbook last semester. Let's see how much of this duplicates on what I had set up for earlier in the slide deck. So we already talked about how computers block our addressable space in 8 bits. So this is just redundant content here. We already talked about how we interpret our binary digits. So say, for instance, our program, say, for instance, our C compiler maintains the type information. That's that context we're talking about. A lot of times it's also why an extension is applied to your files for the virtual block. So when we're running our code, it understands the context in which it should be, and especially as an application goes ahead and extracts from our virtual block of memory, where the underlying machine level program has no regard of that, right? So our system is the thing that provides context. The processor itself sees everything as just binary sequences. So it's our system that gives meaning to the data that exist inside the system itself, inside the hardware itself. Okay, so just some quick basic things. This will probably be a review for most of you. Let's talk a little bit about the different ways we can represent our binary sequences. So we can represent them either starting with the smallest addressable unit, which is a byte, 8 bits. We can either express it as a binary notation, decimal notation, or hexadecimal notation. It's kind of important to understand or just look at what the beginning and ending values are, so you can kind of map it mentally from one sequence to another. So clearly in a binary notation, you're counting values, the number of base values you have is 0 and 1. So if you're trying to encode 8 of them, it will take 8 of those units for 1 byte. Now, if we want to express that in decimal notation, again, we could take the number of bytes and the number of states of those bytes. So you take the number of states, permutation of the number of state changes you have, which is 2, and you could take it to the power of the number in your sequence, and that lets you know what the decimal notation is. So if I have 2 possible outcomes, a 0 and a 1, and using combinatorics, I take to the power the number of possible bits I have, which would be 8, I get then 256. So I can see, I can map between 0 to 255 integer values to 1 byte, which is why when we're talking about the way that we can encode our images, it's mapped between 0 to 255, 0 to 255 and 0 to 255 for RG and B, respectfully, because it's encoding each pixel with 3 bytes, 1 byte dedicated for red, 1 byte dedicated to blue, 1 byte dedicated for green. And then if you have, say, for instance, an image that's 100 by 200 pixels, then you can calculate very quickly how many bytes that's going to be. Okay, and then finally, hexadecimal notation is what we commonly use because it allows us to compress the size of a byte to just be 2 characters. Hexadecimal obviously refers to base 16, which means that we have 16 symbols, countable symbols, before we repeat. So, so just to highlight this, in a binary sequence, the number of symbols we have is 2, it's 0, 1. And then when we want to get 3, we have to then have another lead. It requires more than 1 character to create the number 3, right? In a decimal system, we have 10 countable symbols. And when we get to number 9, we need to add another. We gotta proceed with a second digit in order to be able to have that 10th value, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then 10, which is 1, 0, represents the next unit. We roll over and we reset. Okay, so using that pattern, clearly hexadecimal will have 0 through 9, the same we would have with decimal, but then it introduces A, B, C, D, E, F. We just borrow from our alphanumeric glyphs to represent the other countable units. And then once we get to F, which is our 16th digit, remember we start counting at 0 in actual our counting systems, then we have to roll over and then we would proceed with another value. So here we have a simple table that has our binary values, that has our decimal values, and has our hexadecimal values. The encoding you're seeing here is to get us from 0 to F, and then it's analog in the decimal value and it's analog in the binary value. Okay, let's see. And it looks like we have a comment. It looks like someone had Google searched what a unit inside of the sound data format is, and it might be called a sample. Interesting. I don't work enough with sound data, but it makes me want to play around with it some. Just create like a hello world in a musical audio form. Maybe not musical, but an audio approach. Okay, let's see here. So let's talk about in terms of our hexadecimal notation now, in C, we can have numeric constants that by default are represented in a base 10 system, but we can express numeric values as base 2 or base 16, again, binary sequences or hexadecimal sequences. And what we would have to do is we would prefix the binary sequence with a set of symbols. So if, say, for instance, we preface our numeric value with 0x, and then x can either be uppercase or lowercase, then we can then encode a hexadecimal value. So we can go ahead and store our numerical values in this form here, which then now supports F and A and B and C and D and E all as encodable numbers and not necessarily as letters. Now, did y'all do a lot of time converting between the bases inside? Perfect. Now, yeah, because clearly one of the things that makes a lot of sense is being able to quickly convert between hexadecimal values and binary values and decimal values. The reason why these conversions are so important is that recall the actual state that our data is processed in and that it's actually stored in is in binary sequences. So it's because it's actually manipulating the underlying switches inside the transistor itself. So everything has to have a binary representation. Now, binary representations are huge. Like, it takes up a lot of actual just space. So it's better to encode a binary representation using hexadecimal because each byte only takes 2 characters. Super efficient. But unfortunately, we don't math very well in base 16, right? We've learned to math really well in base 10. So then we want to translate our base 16 values into a decimal value so that we can actually logically think about it. Because unfortunately, we just haven't built the capability of processing on base 16 numbers the same way with the same power mentally as we do with the base 10 system. Sometimes it's easier for us to even take that hexadecimal expression, though, translate it into a binary expression, be able to do some kind of Boolean algebra operation on it and translate it back. Think about what happens if you're looking to like XOR something, or if you're AND something. It's kind of harder to do that when it's in decimal notation. It's kind of harder to do that when it's in hexadecimal notation. It's easier to do that when it's in binary notation, because you can just look at the bit group top to bottom and say, oh, this one goes to 0, this one goes to 1, this one goes to 1, this goes to 0. And so again, this is why it's valuable for us to be able to do these transforms. In practice, almost you never have to do this, right? This is all theory driven. I can't tell you the last time, short of doing some kind of cybersecurity challenge, had to transform my data by hand between a hexadecimal to binary to decimal notation. But it's something that's valuable for you to know because it gives you a better understanding of how these underlying systems work. And these systems are automated really well, but you should kind of know how they're mechanically put together. Okay, so in terms of, so I'll just kind of go through this relatively quickly. To map between binary to hexadecimal, that's super simple, right? Like, I'm sure that y'all have had a lot of training on that because you start with your binary sequence. And so here, a single hexadecimal value can encode up to a 4-bit word, right? So it takes 2 hexadecimal characters to create an 8-bit sequence. And then you can just count starting up, right? So you start at 0, 0, 0, 0. That's hexadecimal value of 0. Then you just kind of do your binary sequence up all the way until you get to like the number 9. And then when you get to 10, that's your A value and what have you. Yeah, there's your full encoding there. Fix binary to that. So it's easy to convert between hexadecimals and binary back to hexadecimal, right? Because you can take each character and then re-express it back and translate it back. So not going to spend too much time with that. Really, I think the most difficult is translating between decimal to hexadecimal. Is that the one that you'd say is the most? So going from binary to hex is pretty easy, right? Would everyone agree with that? Going from hexadecimal to binary is pretty easy, wouldn't you say? Okay, let's think about this. Going from binary to decimal is pretty easy. Well, we'll talk about that. So decimal, we'll talk about with both hexadecimal and binary. So if we want to convert a decimal number to hexadecimal, the best way to do this is you're going to divide by 16, and then you're given a quotient and a remainder, right? And so effectively what you have to do is like long division to reconvert from your base 10 to your base 16. Let's take a look at that. Here, you'll use your hexadecimal digit representing the least significant digit. And so we'll generate the remaining hexadecimal digits by repeating this process. So suppose we had this decimal value of 314,156. Well, we're going to divide that by 16. That gives us a quotient of 19,634, right? So, and then we'll have a remainder of 12. So we capture the remainder because that part is the interesting part to us at this point. The other part is divisible, right? Is divisible, and we can keep dividing from it. So here we're going to go ahead and capture that as our C. And now that's our least significant bit. That remainder is the least significant bit in our sequence. So we're building it from least significant to most significant, right? Now what we can do is we'll take that 19,634, right? And while that's divisible by 16, that'll produce 1,227 with a remainder of 2. So now we use that 2, that'll be our next least significant bit after our C. So then we'll take this, the remainder of this, and then we'll go ahead and divide that by 16. And so that's going to give us a value of 76 as our quotient, and then a remainder of 11, which we can then encode as B. And that'll be our next least significant bit in the sequence that we're trying to translate. Then we'll take 76, we'll divide that by 16, that'll be 4, with a remainder of 12. So then again, we can encode that into a C. Then we take that 4, we divide that by 16, that's 0. Our quotient is 0 with a remainder of 4, so that's going to be our most significant bit. So then if I go then to sequence these hexadecimal values in order, the topmost one, the first one we derived, is the one that starts at the rightmost side, the least significant one. And so the most significant one is going to be the one that's on the leftmost side. So then we would express that as 0x to represent this as a hexadecimal value. That's how we illustrate what base we're operating in. And then 4CB2C. So do you kind of remember this process? Or is this a process that you stepped through at all? Excellent. Yeah, it's a little bit more difficult to go with the base 10 stuff. And then if we wanted to go from decimal to hexadecimal, the way we can do that, so suppose, for instance, we start with our hexadecimal value of 0x, and then the actual hexadecimal digits are 7AF. Then what we can simply do is take each of those values and multiply them by 16 to the power of 2 and add those together. So whereas translating from decimal to hexadecimal was a process of division, this is a process of multiplication, effectively. So here you would take your most significant digit, which would be the 7, and multiply it by the number of units it is. So we have a 0th place, 16 to the power of 0, which resolves to be 1, right? Because anything to the power of 0 is 1. Then we have this, the unit A, which is going to be 16 to the power of 1. And then here we're going to have 16 to the power of 2. So this is a hexadecimal sequence. So just like we can encode, like what is the combinatorial space in a binary sequence by doing the possible number of outcomes to the power of the number of elements in the string or the place of that element in the string inside of our binary sequence, then we can resolve to convert into our decimal the same way. So this is the 0th place in the sequence. This is the first place in the sequence. This is the 2nd place in the sequence. So this is the number of outcomes you have for a hexadecimal value. So, and then this is the actual value it has. And then, so we would then map these values. So notice I'm expressing everything so that you can translate it easily. So this is a mixed sequence, first of all. It's mixed between decimal values and hexadecimal values, right? I did that so that you can parse it. But when we actually start doing any mathematical operations, it's super critical that they're all in the same base. So the next thing I'm going to do is I'm going to translate the hexadecimal values in this next step so that they're actually in decimal value. Then I'm going to resolve my exponential powers so we can see it translates to 256, 16, and 1. Finally, I'm going to actually do the multiplicative property. And then finally, I will just sum those together. And that's how we can translate something that's hexadecimal into decimal. And then every system has a word size. So I mentioned words before in the context that any binary sequence has a length. But the word size, when I say word length, you can have an arbitrary sequence of bits. But a system has a well-defined word size that it supports. Think 32-bit OS system versus a 64-bit OS system. So it's going to be the max number of bits that can be processed at like one within in the way that the virtual address encodes its space. So that's the maximal. The word size represents the maximal amount of like addressable space inside of our memory system. So every system has a word size, and our virtual addresses are encoded using the system's word size. So for a machine with, say, for instance, a W-bit word size, then we can compute the number of virtual addresses to be arranged starting at 0 and going to 2 to the power of W minus 1. Because recall, the actual addressable space is also binary encodings. And it's all based off of a unique binary sequencing to be able to address each thing that can go into memory, right? Every memory address can only be up to a certain length and size. And so whether it's 32-bit or 84-bit is defined on this word size that the system supports. And so in C, which is going to be the language we're really going to be interested in, because that's the one that we're going to build, that's used to build our system, right? We're doing our system development in C. The types of data that we have available are going to be a variety of different bytes, right? So one of the interesting things here is notice that different systems can define different sizes for our data types. So we're not guaranteed, say, for instance, that an int is 4 bytes. There are some systems where that's simply not true, which could cause havoc for code that's designed for a 32-bit system versus, say, maybe a 16-bit system. And so one of the things is that if we have our data types, one of the things you should notice about these data types is that they can consist of multiple bytes, right? So a byte is a single addressable space, but we can start clustering groups of bytes to represent a singular value, right? So if 1 byte is 8 bits, but it only represents being able to encode 256 things, then we can start creating longer bit sequences, but then to store them, we need more bytes. So then the question is, in our system, if we have a block of contiguous memory that represents one binary sequence, let's say a 4-byte sequence, that's what an integer is, or let's say an 8-byte sequence, that's like what a double is. What is the order in which you read that sequence of bits, or those sequence of bytes, or the sequence of bits inside the sequence of bytes? Because they're two different things, right? The bit sequence in its entirety represents an encoding of a value, but then those are blocked off in byte-sized chunks. So did y'all cover this concept of endian, little endian versus big endian? And so the idea is that depending on whether you're starting from your least significant bit versus your most significant bit when parsing. And so this is a consideration that can change from system to system. Some systems will use little endian, where other systems will use big endian. Just if you wanted to know where the concept of endian came from, it's from a children's story, Gulliver's Travels, where there's a war between two factions in a kingdom on what side they're supposed to eat their egg from, the little end or the big end. And they went to war over what end was the appropriate end to eat. So finding the humor in being able to map what order should we read our data in, the computer scientists, you know how they love dry humor, decided to call this concept big endian and little endian. So there's a little bit of like literature influence inside this term, as we're unaware. Excellent. I think we are done today. We will pick up with chapter 2 next class. Oh, we have a question. What is your question?
Hi, I had emailed you, and I don't know if we're allowed to ask about something other than just the lecture today.
If you want to ask me something other than the lecture, go ahead and do so through Discord, actually. I'm going to try to catch up on all the Discords after today's lecture. And that way it impute into the recording.
Okay, that's fine. Thank you.
Okay.
All right.